Hi everyone, I'm George, a PhD candidate from Shanghai Tech University. I'm very glad to share our paper, CLEVEREST, Accelerating CEGAR-based neural network verification via adversarial attacks in this year's SAS. This is a joint work with BBK, SMU, and Shenzhen University. It's really a pity that I cannot be able to see you all in person in your class, and hope you all have an amazing week. So, deep neural networks have demonstrated strong learning capabilities in recent years and has expanded its application to many real-world problems. At the same time, deep learning-based software are found to be valuable to adversarial attacks. So this is what we do in this paper about AI security, a combination of neural network testing and verification. I will start by introducing the adversarial attack, or we can say the neural network testing method, which found that neural networks are not robust to minor perturbations on inputs. If we add some human imperceptible perturbation to the image, the neural network may make a wrong judgment. The image on the left shows that an attack on an image classification task, and the right shows an attack on a road traffic sign recognition task. These attack methods are trying to find counterexamples. They are fast, but cannot provide any probable conclusion. In contrast, different with adversarial attack, which aims to find a counterexample to trigger the bug of neural network, verification methods try to prove that a neural network is absolutely secure in certain inputs or input intervals. Below is a summary of some verification methods. They may be based on SMT, interval analysis, abstract interpretation, or mixed integer linear programming. Although these verification methods can provide probable conclusion that there are no adversarial examples in the specified input interval, it has high complexity. As the aim of an adversarial attack or testing is to find bugs. So we think the combination of testing or adversarial attack with verification in neural network robustness will be very interesting. As in conventional software verification field, combining testing and verification is a common way to speed up verification. So with the aim to accelerate verification, how to select appropriate testing and verification tools and combine them. We give an example in this paper, in which we combine PGD Attack with CEGAR-NN verification framework. I will introduce both of them later. In a nutshell, PGD is an efficient and effective attack, and in CEGAR-NN, we could find a number of sub-problems that could be solved with the help of PGD Attack. Let's give some background knowledge introduction on both PGD Attack and CEGAR-NN below. First, CEGAR. Here is the workflow of CEGAR. CEGAR means counterexample guided abstraction and refinement. The first step of the framework yields an abstract model, which is smaller than the original specification model and easy to verify. This model is consistent on the robustness property with the original model, which means that if the properties of the subtract model are holds or unset, the property of the original model are still holds. If users find a counterexample on the abstract model, then they need to double check it on the original model because it may be a suspicious counterexample. So if it is still a counterexample, then that's good. We can return set. If not, user need to use the counterexample to refinement the abstract model and construct a more processed abstraction. How can CEGAR be applied to neural networks verification? This paper from CAPE 2020 gives a solution. The algorithm is roughly divided into 4 steps. Firstly, the network requires some pre-processing, such as the transformation of the verification property, replication and classification of hidden neurons. These pre-processes ensure that the subsequent correctness of the algorithm. The next step, abstract. The abstraction process merges neurons, which is one of the core ideas of CEGAR-NN. By mergence, you can get a smaller neural network that is easy to verify. The point that guarantees consistency of the property is that this process merging ensures that the output Y is monotonically increasing. So if the property is Y is bigger than a constant C, the framework is sound and will never give a wrong result because Y is always increasing during the abstraction, during the neural merging. For example, when we deal with the weights and bias on a positive neuron, only add and max operations are executed. And then ReLU activation function inside the network ensures that the output of each node is greater than 0, is bigger than 0. So this ensures the correctness of this algorithm. Then CEGAR-NN uses the neural network verification tool, myriad, an SMT-based verifier to check the property on abstract subnetworks on abstracted models. If refinement is required, the previously merged neurons are split. So here is the algorithm for CEGAR-NN verification framework. The input is a tuple, P and Q, where P is a precondition, or we can say this is a constraint on the inputs, and N is neural network. Q is a postcondition, which is a property to be verified. Now, let's look at where we can optimize the framework with testing. First is the line 1, the process of initial abstraction. In the original CEGAR-NN paper, the authors recommended a one-step process to reduce the initial network to obtain a minimal abstract model directly. But we think that we could use testing algorithm as an indicator here. We can make abstraction gradually until testing can easily review a counterexample to validate the property P, to validate the property Q. This seems like an early stop. We can use testing algorithm to find when we can stop the initial abstraction operation. Then is the third line. As the abstraction is essentially an over-approximation, which makes it easier to find the counterexample in a new model. So instead of invoking complex verification tool in the subnetworks, we can first consider to use an attack. In other words, use testing to search this subproblem, to search on these submodels, and try to find a counterexample before calling the SMT solver. So this is the 2 points we find that in CEGAR-NN framework can be optimized by testing. Now, back to the background part. Which testing method, which attack algorithm to choose for the acceleration? The test method needs to be efficient and effective, as I said before. We choose PGD, projected gradient descent attack method. The reason is that PGD is almost only use the first order gradient for optimization. It is very efficient. This is an iterative attack. Line 4 to line 10 being the iterative process, where each iteration simply uses the sign or the direction of the gradient to update the input in line 9 and line 10. And we can say that in the first line, the second line, and the third line, this is the reboot mechanism with random starting points. That is very important because it could avoid starting local optimal and guarantees the success rate of the attack. Of course, in order for PGD to work properly, with the verification problem. We also need to make some simple transformations to the triple PNQ, such as we should use P as a constraint on the input and transfer Q to a loss function. With each subformula, there is a transformation of properties, just like the limitation of the lower bound and upper bound. When the loss is 0, it means that we have found a counterexample. And if we want to verify more than one property, we can multiply them together. So this is our loss function for PGD attack. So turn back to the CEGAR algorithm. Compared with the original CEGAR-NN, we take advantage of the PGD adversarial attack to get an early stop the initial abstraction in line 1. We use a very small time cost to perform a simple test of the counter neural network after each abstraction. And we also store previously generated samples for review of the subsequent abstractions. So this is the first optimization. And then we also use PGD adversarial attack to test the abstracted model before calling an SMT solver. In contrast to the previous CEGAR, a verify, check, and refinement process. We use test, check, and refinement to minimize the use of an SMT solver. We only try to invoke SMT solver when the PGD attack fails to find an adversarial example. So we replace the line 3 to a test, check, and refinement process in CEGAR. Let me use a concrete example to show how our approach works. For the sake of intuition, here we use the symbolic interval analysis as a backend solver of CEGAR-NN instead of the SMT solver I mentioned earlier. This is a very simple 3-layer neural network. And before being abstracted, we can obtain a formula for the output Y with respect to the input X. We just calculated the V1, V2, and V3, and we got this. Subsequently, we apply the rules of CEGAR-NN to merge the top 2 neurons in the middle hidden layer. Because the process ensures that our output is monotonically increasing, so we choose the max bias between V1 and V2 as a new bias, and the output weights are obtained by adding. Then at this point, the formula regarding to the output Y will also be changed from this to this. If we assume that the input interval for both X1 and X2 is 0 to 2, then we can easily calculate the upper bound on Y before and after the abstraction. Suppose that the property we want to verify is Y is bigger than 20. Then obviously, these two models return different results. One is unset. This is one unset, and one is set. Where the abstraction simplifies the model, the over-approximation introduces some suspicious counterexample. So if we use some testing algorithm here, we will easily find counterexamples and yield results. I think when X2 equal to 0, any X1 bigger than 1 is a counterexample here. So no further abstraction is needed, or we can avoid calling complex backend SMT solver. Then the experiment part. We conducted experiments on the airborne collision avoidance system benchmark. We select 45 models and more than 22 verification properties that have been widely used in previous neural network verification work. So we verify a total of over 1,000 cases. The results are shown below. Here, each point representing the specific solving time of a verification case, and the line represents the number of cases solved over the time. So if the blue dot appears to the left, the upper left of the right dashed line, it means that our method is faster than CEGAR-NN. It can be seen that our CLEVEREST are better than the baseline method, CEGAR-NN, in terms of efficiency and the number of solved cases. The number of solved cases can be shown by the line. Yeah. By the way, the unset results and set results shown separately. Unset means that the property holds, which means that the SMT solver must be called once because we cannot return unset by test process. So it doesn't look like that our method do not achieve a great advantage, as the last query of SMT solver will take up most of the time. However, it can be seen that for set cases, which means that a counterexample exists, our method can be far ahead of CEGAR-NN. Here are some more specific results. To check clearly the contribution of our method on the unset case, the figure on the left, which refers to the time computation of the solving time excluding the last SMT solver query. It shows that attack has a huge time advantage over SMT solver when solving the abstracted sum models. This figure shows that our test, check, and refinement process can a big advantage. The right is the average number of SMT solver calls for the unset case. ATT means our attack-guided abstraction, and the CLEVEREST means our test, check, refinement system. Since the unset case, as I said before, must call SMT once, it can be found that we have almost reached the optimal value on the current benchmark. We have also carried out ablation experiments for both of our two optimizations in this paper, demonstrating that both of them are effective. So I think that's all of our algorithms and experiments results. I hope our method is easy to understand. Finally, I would like to share some insights during the experiment. Alpha Beta Clone is a winner of the last 2 years neural network verification competition tool. So it uses a simple combination of testing and verification. They use an adversarial attack, try to find adversarial examples before calling the verification tool or after running an incomplete verification tool. And if set, they can just return, while our approach does testing and verification combination in a more elaborate way. We also hope to facilitate the combination of the two approaches, testing and verification, in more ways in the future, and to experiment with more data sets. For example, we're really curious about could the testing info to help branch and bound verification methods, can attacks and CEGAR be used as a fuzzing framework of neural network training framework, or neural network verification framework, as tests can generate inputs and CEGAR could be treated as a test oracle, utilize the consistent on the property. We have also made some other attempts previously. We have tried to use the intermediate results of verification to evaluate the difficulty of testing. And based on this, we won a 3rd place in last year's CVPR workshop competition. So in summary, in this paper, we have proposed a new CEGAR-based framework, CLEVEREST, for neural net verification by synergistically combining testing and CEGAR-based verification techniques. We have implemented our methodology. The extensive experiments demonstrated the efficiency of our methodology. Although we have only done a combination of PGD and CEGAR-NN, we try to explore the possibilities of using testing tools within the verification method. And we hope that our work will inspire more related explorations. I would like to thank all the reviewers for their comments during the review process, and thanks for your listening. If you have any questions, please feel free to contact us. Thanks.
Hello. Oh, hi.
Yeah, hello.
Thank you so much for the talk. So I think the experiment you showed just now was on rather small scale networks. And do you think your tool has the potential for GPU deployment for even better acceleration? Thank you.
Okay. Let me turn back to there. Yeah, this is really a good question, and this is what we want to do. But I have to say that it's a pity that we cannot show these results on the paper. The question is that, so could we use our CLEVEREST framework on bigger data sets, bigger neural networks? One thing I want to say is, if you want to apply testing on a bigger data set, on a bigger model, it is much easier than use verification on big neural network, big data sets. So I think CLEVEREST have the potential to do this problem. But the reason why we didn't do this kind of experiment in this paper is that currently the CEGAR-NN we used in last year cannot deal with this kind of problem. So at first, they will expand the neural networks for abstraction and then compress the scale of the network. So this is a problem of the verification tools. But I think CLEVEREST have the potential to deal with them.
Wait a minute. We were disconnected, so can you start the answer again?
Okay.
We could not listen to you. I mean, we just have been reconnected. So
okay. So you can hear me now?
Sorry? Yeah, we can hear you now. You should start the answer again. Sorry.
Okay, sure. This is a good question, I have to say. Yeah. And this is what we want to do in our paper, but it's a pity that we didn't do it as some experiments of another paper didn't finish, so we didn't show the results here. And the question is about is CLEVEREST has the potential to do experiments on more bigger data sets or bigger neural networks. The first point I want to mention that testing, if you want to apply a testing algorithm in bigger data sets, bigger neural networks, it's much easier than a verification algorithm on a bigger neural network or bigger algorithm. So I think CLEVEREST have the potential. The reason we didn't do this kind of experiment in this paper is that based on the last year's CEGAR-NN, they cannot handle this kind of problem. So we are upgrading on CEGAR-NN. So this is a bottleneck, and we didn't do this kind of experiment. But I think CLEVEREST all testing algorithms have the potential to handle this. I know there are several follow-up works about CEGAR-NN, and now they can handle other data sets just like MNIST, CIFAR-10, and so on. So I think we will consider to do this later or implement CLEVEREST on more CEGAR-based verification frameworks. So this is an answer.
Okay, thank you. Is there any question? Any other question?
Hey, very nice
Yeah.
work. It seems like in your abstraction refinement loop, you are creating multiple neural networks, right? So,
Yes.
my question was that, let's say, what happens is that when you are actually developing neural network, you just don't stop once. You train a neural network, you test whether it has some property or not, and then if it does
Yeah.
not, you repair it again or do certain things, right? So, I'm just wondering, like, somehow can you extend this technique that you can give proofs for multiple networks at the same time instead of like verifying
Uh,
one.
okay. Uh, this is a good question, and I have to say we didn't consider about this before, because during the experiment we didn't treat the abstraction process as a pipeline, which means that they merge several neurons in the same time. We did it step by step, so we didn't consider about this problem. But I think we can handle this problem by that. As I said before, we storage the samples generated during our attacking process. So one of the time you merge several neurons in the same time, you can call the previous generated counterexample to check the model firstly. Then if you cannot find any counterexample, then you call the PGD attack to check it again, or you can say that in every separate neural merge process, you put the check with the previous generated examples in the loop. After you merge every pair of neurons, you just call the function and check it, and in the last you call PGD attack. So I think this is a potential solution for your problem, but I have to say that we didn't consider about this before.
Oh, thank you for your answer.